Hello everyone, welcome to the session. We'll continue to solve more number of problems which are asked in GATE, ESE and Tspsc. And we will start with ESE problem which is held in 2018. A 150 mm diameter shaft rotates at 1500 rpm with a 200 mm long general bearing with 150.5 mm internal diameter. The uniform annular space between the shaft and general bearing is filled with the oil of dynamic viscosity, which is like 0.8 points. Here the shear stress on the shaft will be, and here the options is 1.77 kilonewton per meter square, 2.77 kilonewton per meter square, 3.77 kilonewton per meter square and 4.77 kilonewton per meter square. And here the first thing we have to see from the problem is what to find. Here he is asking to find the shear stress, and we know the formula of shear stress in properties of fluids from the Newton's law of viscosity, which is tau equals to mu into V by H. Okay, now what is mu? Dynamic viscosity. Already the value is there, which is in terms of poise is there, but here we require the answer in Newton per meter square. For that, what you're going to do is convert this into Pascal second, and later what you're going to get is Newton per meter square. And first the dynamic viscosity convert into Pascal second. To convert that into Pascal second, just make the poise divided by 10. So what you're going to get is 0.08 Pascal second. 0.08 Pascal second. And the next what we require to find is velocity, and the next one is height of your fluid which is filled in the space between the shaft and the bearing. And coming to the velocity, here the equipment is like a shaft and it is rotating with some rpm, right? For the velocity what we required is, here in the given data we don't have any direct velocity, but he given like 150 rpm, and moreover it is a shaft which is rotating, right? It is not a linear one, it is a rotating one. And for that rotating we have a relation between your linear velocity and the angular velocity, which is V is equals to R into omega. And what is this omega? Angular velocity, and this one is radius of your shaft. And what is the diameter of the shaft? 150 mm. Convert this into meters. What you're going to get is 150 into 10 to the power of minus 3. But for the radius, what you have to do is 150 divided by 2. What you're going to get is 75. 150 divided by 2 is equals to 75, and the radius is 75 mm. But to convert that into meters, just make that into 10 to the power of minus 3. What you're going to get is radius in terms of meters. And coming to omega, here it is like 2 pi n by 60. We have a formula. And what is n? N is given, which is like 1500 rpm, right? You just substitute that value here, you're going to get the final result. Okay, we'll check that later. And coming to here, substitute all the values, and coming to this h1, okay, h is equals to t1, which is diameter of the shaft, minus d diameter of your bearing divided by 2. Okay, thus the height we require. Just take like this, which is like diameter of your bearing and the diameter of your shaft. Then what you're going to get, 150.5 minus 150 divided by 2. So just calculate this, you're going to get 0.25, and this is in mm. Convert that into meters. What you're going to get is 0.25 into 10 to the power of 3 minus 3 into 10 to the power of minus 3, and this is your h value. Now take these values, which is like dynamic viscosity in Pascal seconds, and this is your R in meters, and 2 pi n by 60, which is 2 pi into 1500 divided by 60. And if you substitute that in these, and moreover h equals to 0.25 into 10 to the power of minus 3, what you're going to get is 3.77 kilonewton per meter square. Just calculate all these values. Okay, we'll see that tau is equals to mu into V by h. So finally what you're going to get after calculating all this is C, which is 3.7 kilonewton per meter square. Okay, we'll see the next problem. And this problem is asked in GATE Civil Engineering 2016 in set 2 for 1 mark. Here we have two groups, which is like group 1 containing the type of fluids, while group 2 containing the shear stress, shear rate of shear relationship of different types of fluids as shown in the figure. So now we have two groups, which is like group 1 and group 2. Just we have to match all these by seeing this figure. This figure is also given the problem, and we have to correct the match between group 1 and the group 2. Okay, so whenever you're going to get these type of problems, then don't start from your B or don't start from your S. Okay, first check out the check out the options. For example, here option P is fixed like P2, P2, P2. Don't check that, just leave that, because we already have the direct answer for it. So P is directly 2, so you just cancel it, it's over. Your curve is over. And coming to Q4, here it is like different, but it is like common. You just keep that in hold. And for R and S we have different values, right? So if you start with the R and S, so it will save your time and it will be easy, and in the fast way you can solve the problem. And coming to the plastic fluids, from these are the graph between your shear stress and the rate of shear. And for the plastics, we already know that for the plastics it will travels like there is no rate of shear, but after passing through the yield stress, okay, the rate of shear strain is similar to your shear stress. That means shear stress is directly proportional to your rate of shear, but we required some yield stress for it. So the plastics will follow this curve, which is 5. So for R it is like curve 5. So where is R5? Here we have the R5, right? Okay, we know what is P, and now we'll try to see this S, which is dilatant fluids. For the dilatant fluids, your curve is 3, right? And your 4 is pseudoplastics, and this is for Newtonian fluids, and this is for non-Newtonian, or we can like Bingham plastics or plastic fluids. So finally, for Newtonian fluids you will got 2, and for the pseudoplastics you got 4. So for plastic fluids you got the curve 5, and the dilatant fluids you got the curve 3. So all these options are there in the C, right? We'll see the answer. Okay, the answer C is right. And coming to the next one, and this is your CATE for mechanical, which is held in 2006, and it is also asked in 1995. And the question is, for your Newtonian fluids, you have to select the best which is suited for the Newtonian fluids. And the option A is shear stress is directly proportional to shear strain. Is it right? Is shear stress is directly proportional to shear strain for the Newtonian fluids? No. And coming to the rate of shear stress, we not at here in the Newtonian fluids, so it is wrong. And coming to the shear stress is directly proportional to rate of shear strain. Yes, this is the right one. But once again, we'll check the D also. Rate of shear stress. We don't have such a word in Newtonian fluids or in properties of fluids. So, okay, the C is correct. Answer C. And coming to the next one, and this is your ESE 1996. Here we have the two lists, which is list 1 is for fluid properties and the list 2 is related to the terms. That means what properties are related to, and select the correct answer using the codes given below. And this is your list 1, which is capillarity. Second one is vapor pressure, and the viscosity and the specific gravity. And these are the related terms, which is like cavitation, density, density of water, shear force, and the surface tension. So now we'll select for the capillarity. Okay, the capillarity is due to what? Okay, is due to cavitation? No. It due to density? No. And it is due to shear force? No. It is due to surface tension, right? So for A it is 4. For A it is 4. So just now I said, so when you got such a options, don't go with that. Just leave these A and B, and now you go with C and D. By that you directly get the answers. So now I just want to go with this D, which is specific gravity. Specific gravity means it is density of water divided by some density of liquid divided by the density of water, right? So I will go with this option, which is like specific gravity is related to density of water. But anyhow, we'll check out whether it is there in these options. D is 2. Okay, here we have, okay, why? Because we got this 4 for the capillarity, and for that we have the D for 2 for D. And coming to the viscosity is due to shear force, right? Okay, we have that option. So now you can save the time here. Okay, you can save the time here. You should not check this. Why? Because these two are related, sequence is there, but here we get some confusion with whether it is 2 or 3. So we solve this, we know this, and if you leave this, your direct answer is D. Okay, and this one is asked in Tspsc, which is AEE, held on 2015. And the question is the relation between surface tension and the difference of pressure between inside and outside of the liquid drop is given by. So simple, try to solve this. Don't confuse with these whether it is sigma 4D or 8D 6D. Don't confuse with that. It's a simple problem. Here we have your liquid drop, and the pressure is acting in this way. So if you want the concept of this, just go with my previous videos of properties from 1 to 6. The classes is there. You can go through that. You directly have the derivative part of these, how to solve, how to get the pressure differences for the liquid drop, liquid jet, and the soap drop and soap bubbles. Okay, and if you want, you can check my playlist. And coming to the problem here, just think that this is your liquid, and at the center it is having some pressure which is P, and this is acting for the area pi by 4 d square. That means the area of your liquid drop, pi by 4 d square, and this is the total area of your liquid drop. And on these surfaces we have the surface tension, and the area of or circumference of this particular liquid drop is pi d. And from the equilibrium principle, these two forces, which is surface tension force and the pressure force, will be equal. And what you're going to do is P into pi by 4 d square, that equals to surface tension into pi d. So now you can simply cancel this d square, pi and pi. Finally what you're going to get is p is equals to 4 sigma divided by t. Okay, so now your option is C. So for the relation between surface tension, the difference of pressure between inside and outside of your liquid drop is 4 sigma by d. Okay, answer C. We will continue in the next session. Thank you.